Hello class, welcome back. Today we're going to go ahead and continue our sections. Right, today we're going to go ahead and complete homework I, right, which consists of section 5.1 and section 5.2? Yes, 5.2. Right, so let's go ahead and get everything ready. All right, so summations, all right? Find the value of the summations, all right? So, right, reading summations, right? This is what this here stands for, sum, right? So let's go ahead and do a simpler one, right? Let's just say I want you to find the sum starting at k equals 1 all the way up to, we'll say 4, for a function that is x, we'll say k squared. Right? Right, so this means you're going to start at the bottom value and you're going to go all the way to the top value, right? That is where you'll stop, right? So for the summation, right, I'm starting at 1 and you're plugging it into that function, right, that you're given. So that's going to be 1 squared plus 2 squared plus 3 squared plus 4 squared. And that's where you would stop, right? So this is 1 plus 4 plus 9 plus 16. All right, so this is 5 plus, what does that give me? 25, which is 30, meaning the summation beginning at k equals 1 all the way to 4 of k squared is 30. All right, this is the same thing we're going to be doing now, but with this trig function. All right, so here I have cosine of pi times 0 plus cosine of pi times 1 plus cosine of pi times 2 plus, all right, I'm going to do this all the way, right? And let's go ahead and do one more. There's a reason why I want to do a few more with these. Cosine of, there we go. Yeah, we'll do that one. Pi 3 plus cosine, yeah, we'll do that one. Cosine of pi 4, right? And we're going to go all the way up on, we reach 18, right? So yes, you do have to go ahead and provide all your work, right? Cosine of, what is that? 18 pi 18, right? 18 pi, same thing. Right, so we have that, right? This is just cosine of 0 plus, why am I writing sine? Cosine of pi plus cosine of 2 pi plus cosine of 3 pi plus cosine of 4 pi plus, right, all the way to cosine of 18 pi. Oh, this is bothering me. Right. You know what this is, right? And you'll find out exactly what is this cosine doing. This cosine value is going to be oscillating at these points, right? Cosine of 0 is 1. Cosine of pi, right? That is what? -1. What is cosine of 2 pi? 1. Right. What is cosine of 3 pi? Right. Do it for all of those, right? And you, for this example, try it out. You should get the answer 1. Right, you should get the value 1. So that's pretty much all we're doing, right? We're going to be adding all those values, right? Going to be adding all those values. Right, you find out that between 0 and 1, right? Between 0 and 1, that cancels out. Between here and here, that cancels out, right? And we have 18 of them, right? So between 1 and 2 cancels out. What am I doing? 1 and 2. 2 and 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Leaving you just with an 18. All right. Leaving you just with an 18. This was right. Ones minus ones, ones minus ones. This is the one that starts in this pair, right? Leaving me with just a 1, nothing else to cancel out on. All right. this section is going to be very important, especially whenever you're looking into calculus 2, right? You're going to have a full exam, probably even exam and a half, right? Dealing with this, right? And if you're an engineer, you're definitely going to be seeing this, right? You're definitely going to be seeing these, all right? So here I'm giving you the answer, right? Here I'm giving you the answer, the answer laid out, and you need to tell me, all right, how far does that go? Right? How far up does it go? All right. So you want to create an equation such that you start at the number 6. Then whenever you plug in your next value, your value of n, you get 9. Their third value you plug in, you get 12, right? So there's always going to be a pattern here, right? There's always going to be a pattern here. You do know that all of these numbers are separated by 3. 3, all right? So here you could say 6 plus 9 plus 12 plus 15. What would be that? Plus, what's plus 3 more? It's 18 plus 21 plus, what's the other one? 24 plus 27 plus 30 plus 30. What was that? 33 plus 36. So that's exactly what it is, right? We end up at 36. And with these, honestly, the more you do these, the more of these that you do, the better you're going to get at finding these equations, right? I really don't know any other way, right? I'm sure there's probably another way out there, right? But me personally speaking, it came through experience, right? You're seeing so many of these that you're able to just, by trial and error, see it in your head. All right, so yeah, all right. So here, right, you want to start off with n equals 1, right? With n equals 1, right? If you were to do 6n, sure, right? If you were to say, hey, the function I'm using is 6n, well, for n equals 1, right, this gives me 6 times 1. Very, very nice, right? So that gives me 6. But what happens at n2 for this one? That's n2. This is 12. Nope, the second one should be a 9, all right? Right, so definitely pause the video, all right, and try to find one. And you're ready. And with these, there's generally more than one, all right? There's generally more than one. If you were to submit this, I'll accept more than one answer, right? So here, right, we end up you find out that the function 3 plus 3n works, right? If you were to plug in n equals 1, you get 3 plus 3 times 1, which is 6. All right, so this here is your starting point. And as your n values increase, this is what you're going up by. You're going up by 3. All right, and I see this pattern here, right? So whenever I did this, I knew that this was going to be 3 times something, all right? 3 times something. Right? And what n are you going to stop? Well, this is for n equals 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? At 11, right? So my summation function should look, right, from 1 through 11 of, right, you want to write this in parentheses, 3 plus 3n. Right? Wrapping it up in parentheses is very, very, very important, right? Very, very nice. An important part of this section. Whenever you're dealing with velocity, and let me start off with this. To take the integral is to find the area under a curve. That is all we're doing. Let me say that again. To take the integral of a function between a certain point and another point, it is to find the area under that curve. If you're giving a velocity function versus time, right? You have this graph here. It's a graph of velocity versus time. If you take the integral, or if you take the area under that curve, it's going to give you the total displacement, the distance traveled. Remember, there is a correlation between position, velocity, and time and acceleration, right? If you're at velocity and you take the integration, it gives you position. All right. If you derive position, it gives you velocity. All right. So here, hey, this is a function, an object moved with this velocity over the given amount of time. You want to know how far did the object travel, all right? How much distance was covered between 0 seconds and 45. And here you want to use algebra. This is generally what you want to go ahead and do, right? You want to break down shapes into squares, rectangles, and triangles, right? So I would split this into a square here. I mean a rectangle. I'm going to do that shape. And then I'm going to break that down into a triangle. All right. For my rectangle, right, the area is just base times height. For a triangle, right, it is a triangle. Remember what we said, a triangle is just half of a square, right? It's half of a rectangle, right? So that's just going to be base times height over 2. Right, so looking at my rectangle, the base is 45 times my height is 1, meaning the area for that rectangle is 45. For the triangle, the base is 45, and my height is, remember, it's not 3, because I know you're probably going to want to read 3, but it's not 3. It is the distance between here and here. Right, it's a distance of 2 units. Or in other words, 3 minus 1, right? Final minus initial, 3 minus 1. So that's going to be times 2, all over 2. Right, 90 divided by 2, or these two cancel out, giving me 45, meaning the total area is 45 plus 45, which equals to 90, meaning, right, since velocity is dealing with feet per second, the total distance traveled by this particle or by this object is 90 feet. Pretty neat, huh? Pretty awesome. Okay, we're going to be finding areas under a curve, right? We're going to be finding areas under a curve using what's known as right endpoints and left endpoints, right? So without a graph, right, you are given this function and you're told, hey, you have this curve. I want you to find the area between 3 and 5 using endpoint approximation. So it's not going to be the exact answer, but it's going to be pretty close, all right? And they want you to use 4 subdivisions, all right? So generally what I like to do is create a number line, all right, where it's 0, 1, 2, 3, 4, 5, 6. And I'm focused between 3 and 5, right? I'm focused between this, and this. All right, I'm focused between there and there. And I need to split this into 4 subdivisions. All right, I'm going to have to split this into 4 subdivisions. So I need to go ahead and know what is the distance, right? Guesstimating this, right? This is going to look, the halfway point, I know it's going to be, what, 4.5? All right, and if I were to split each side again, right there, that's going to give me the 4 subdivisions that I'm looking for, right? But you need an exact value, right? I need to know exactly what is this distance here between 3 and forward. All right, how you find that distant x is by this formula here. Delta x is equal to b minus a divided by n, all right? Where a and b are the endpoints that they give you, right? From here to here, so from a to b, and your n are your divisions, right? Your subdivisions. So here, this is going to be 5 minus 3. Oh, I'm sorry, I did 6. I'm so sorry. I did 6. This is going to look much nicer, right, for this example. The halfway point is going to be here, and the midway points are going to be 3.5 and 4.5, right? But we won't know that all the time, right? All right, so 5 minus 3 over 4 is 2 over 4, which is 1/2, right? Meaning between 3 and this division, it's 1.5, meaning this point here is going to be 3.5. Add a half over here, that gives me 4. Between here and here, right, this is going to give me 4.5. And between there and there, it's going to give me 5, right? And you need to write down these points because they're going to play an important part, right? Since we're using right endpoint approximations, you're going to look at your closed area, and you're going to start at the far right, and you're going to count your walls, right? Meaning, I'm going to start at the very right because I want to go ahead and include. I'm doing right endpoint, right? So I'm going to include this point 5. I'm going to include this point 4.5. I'm going to include this point 4. And I'm going to include this point 4.5. All right. You may be asking, hey, what would I do if I get the left approximation? Well, if you get the left approximation, you would do the same thing, but you're only looking at the left. Right, so if you got left point approximation, you would start at the very left part of your wall, and you would include 3, 3.5, 4, and 4.5. All right. So just the points that are shifted to the left. All right. All right. All right. So now I'm going to go ahead and start and plug it into this formula that I plugged on the top. You're gonna if you're doing the right endpoints, you're gonna start from the very left one that you have. For ours is 3.5, right? So in other words, my x1 value is going to be 3.5. My x2 value is going to be 4. My x3 value is going to be 4.5, and my x4 value, right, is going to be 5. I'm going to plug it into this formula. F at x1 times delta x plus f of x2 plus delta x plus f of x3 times delta x plus f of x4 times delta x. All right. So what is my function? We know what our function is. That's what was given to us. It's x squared. All right. So it's going to be x squared times delta x, right? So that's the function we're using. But what are we plugging into x squared? We're plugging x1. So this is going to be 3.1 squared times, what's delta x? 1/2. Plus my function at x2 times 1/2. Plus my function squared times 1/2. Plus my function 1/2. All right. This here is going to give me an approximation. All right. This here right there is going to give me an approximation. Okay, let's see what this ends up giving me. All right. 3.5 squared. Oh, sorry. Let's go ahead and plug all this in. All right. Yes, another thing you can do, right, is you can factor out the 1/2 and just do 3.5 squared plus 4 squared plus 4.5 squared plus 5 squared, right? That's a value they all have in common. All right, so let's do all right, and I got 36.75. All right, so that is the area under that curve, 36.75. Right. If you were to use left endpoint approximation, you wouldn't start at x equals 1, right? You would start at x equals x naught, right? X naught, right? X to the 0. So in other words, if you're labeling these, right, starting from the very far left, this is x naught, this is x1, this is x2, this is x3, and this is x4, right? When we used right point approximation, I use the far right points, right, for right side approximation. If you were using left endpoint approximation with 4 subdivisions, you'd be using the far left points. So always start at x naught, right? Always start at x naught. Very nice, right? Very, very nice. Right, so here for this problem, right, it's graphically, and I wanted to go over these graphically with the graphic ones as well, right? Like, well, what exactly are we doing, right? So I need to find the area under the curve below for x equals 1 and between x equals 1 and x equals 6, right? So that'll be between here, right, and between here. All right, using 5 subintervals, right? And you'd see that 1, 2, 3, 4. I can go ahead and create four rectangles, right? Between here and here. Right, so if I were to split this into, split it like that, you'd see that I have 1, 2, 3, 4, 5, right? I can create 5 rectangles. With left endpoint approximation, you're going to start at the very far left, and you're going to go up until you hit the line, and then you're going to go to the right until you hit the next subdivision. Meaning, right, you're going to go here, you're going to go up, and you're going to go over like that. All right. The next one, you're going to go up, hit it, and come back. You're going to go up, hit it, and come back. All right. Next step, you're going to go up, you're going to hit it, and come back. And it stops at 6, right? You're going to go up, hit it, and come back. Right, and you'd notice that these rectangles are under my curve, right? Meaning there's some stuff that's not gonna be included, right? So in other words, this is going to be a lower estimate. All right, so let's just say if the answer for this was 5, my answer is probably going to be like 4.7, 4.8, right? You might be asking, what happens if I would have done the right point approximation, right? So that means you would go up and then you go to the left. Right, or you go to the left. So in other words, you would go up, you start at the right, you hit it, and then you go to the right, go down like that. Right, you would go up, hit it, and go out like that. You would go up, hit it, go like that. You would go up, hit it, go like that. Then you would go up, hit the line, and then go down like that. What's the difference between this one and the last one? Well, for this specific graph, doing a right endpoint approximation, it's going to be an overestimate, right? Again, if my area was 5, I'm including more than I should, right? So this is probably going to be like 5.2, 5.3, all right? So let's go ahead and do the underestimates, right? So after you do these triangles, you're going to ask, right? You would ask, what do you got to do now? What you're really doing is finding the area under these rectangles, right? So for my first subdivision here, the height is approximately what? 1.1. Let's do base times height, right? So my base, my distance is 1 times my height, which was what, like 1.1, plus my second rectangle, which is about what, 1.5. My base is 1, and my height is about what we said, 1.5. All right, my base is 1 for the third one, and it's not just 2, it's about what, 2.9, 1.9, plus, right, for this fourth one, it's about, what would we say, 2.2, base 1, height 2.2, and last but not least, my base is 1, right, and these are guesstimates, right? We know my open math is a little bit picky, but as long as you're within the area, right, you're fine. As long as, right, you're fine. If it doesn't take it, I'll still give you credit based on your work submitted, right? And then the last one should be what we'll say 2.4. Right. You go ahead and add all these up. right? And I get approximately 9.1, all right? All right, but it should be pretty close to this, right? If for some reason you got a 4 or 27 or something, that's kind of off, right? That's pretty off. But as long as it's close to 9, right? As long as it's close to 9. All right. And again here, right? Here we have another way we can apply a formula, right? Using 10 approximations. Whoa, right? You're fighting 10 approximations, approximating rectangles and find endpoints. So in other words, my A is going to be -1. My B is going to be 2. My N is going to be 10. My delta X. All right, this is going to be B minus A over N, which is 2 minus -1 over 10, which is 3 over 10. All right, 3 over 10. That's what my delta X is going to be. All right. That's what my delta X is going to be. All right, so you may be asking, how do I find those endpoints? All right, how do I find those endpoints? Well, I know I'm starting at -1. We'll say 0's there. We'll say 2's here. All right. So this is about my high point, my endpoint is there. This is going to be 1, 4, 5, approximately there, right? That is about the halfway point. Then the next one should be 1, 2, 3, 4. All right. Then if you notice, I have should have 10 rectangles, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? 10 spaces. Right, where this is x0, this is x1, this is x2, this is x3, this is x4, this is x5, 6, x7, x8, x9, and x10. All right. Very nice. All right, so you may be saying, hey, what are these points up here? Right? How do I find that point? X1. All right, so in other words, you're going to get -1, and you're going to add 3 over 10 to it, right? Because you want to know from from there to there, how much is it, right? How far am I? How am I from there, right? If you have your calculator, of course, right, you use your calculator, all right? If not, by hand, right, which really shouldn't take long, all right? All right, this here you find out gives you. Go ahead and write all these out for you all. The -7 over 10, all right? -2 over 5, -1, 10, 1/5. All right, the other one should be. Ooh, actually, this is not. 0 is not my x5, right? 0 is not my x5. The next, my x5 would be 1/2. All right, plus 4 over 5 would be my x6. 11 over 10 would be my x7. Right, and the reason it wasn't 0 is because it's not symmetrical, right, between -1 and 0, using bounds of 3 over 10. So 11 over 10 plus 3 over 10. This gives me 7/5. Ooh, where's my 1 value? That's why it was kind of throwing me off. Also, 1 was back here, right? 1 was approximately here. Let's go ahead and move these guys up the way. There you go. 17 over 10 and 3 over 10, right, would give me 2. So those would be your points, right? This here would be your points. And again, all right, you should, you do know that whenever you add the last one, you should end up at 2. If you don't, then something's wrong with your endpoints, right? But always start from the very left and just keep adding until you end up at your goal, right? And all you need to do now, right, since you're doing what, right endpoint approximations, you're going to use the farthest right 10, right? So you're going to be using 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 for those, right? Right. So for right and approximation, you would use those points. If you were doing the left endpoint, you'd be using these points, all the ones to the left, with the exception of the last one, right? Exception of the last one, right? Where your function is 1 over x plus 3, right? So in other words, you would be plugging in, you can do it this way, right? Delta x by f of, we're doing right approximation. Let's do right endpoints, right? So it would be x1 plus f of x2 plus f of x10, right? So in other words, how this would look like is delta x is 3 over 10 times my function at that first endpoint. So this would be 1 over negative 7 over 10, all right? 3 plus 1 over that second endpoint, negative 2 over 5. And yes, please, you would have to use fractions, all right? Do not use your decimal points. Plus 3 plus, right, plus the function with 2 at the end, right? So this would be 2 plus 3. Right? And keep track of your middle values, right? These middle solutions, because whenever you do the right endpoint, you're going to be using the middle parts again, right? So you don't have to do extra work. That computation value has already been found, right? So literally the first one and the last one are the only ones you need to go ahead and do uniquely each time. Very, very, very nice. All right, so how does this apply to definite integrals? All right, what we learned before was the integrals that were not defined, indefinite, right? They were not defined. It was just, hey, you have an integral, boom, integrated, and you had to add plus c, right? For these definite integrals, you are defined. It's saying, hey, it's between here and between here, all right? It's between there and it's between there, right? So, right, you're giving the summation, right? You're here, you're giving the summation, and you're being asked, hey, how would you write this in an integral, right? Right. Well, my bounds are going to be from a to b of a function. Right. For here, it is between 3 and 8 of my function, right? Which is, right, and of course, you want to write this in parentheses, for cosine of 2 pi x plus 5. All right, plus 5. And that's how you would write that as a definite integral, as an integral that is defined, right? And why is this helpful, right? You might be saying, well, what is this helpful? Let me go ahead and do an example. Let me go ahead and do an example. Well, let's do it above here. All right. So I created this function in Desmos, right? Let's go ahead and clip. Let's go ahead and clip this. All right. All right, that's what my graph looks like. I have this is y is equal to x plus 2. It's a simple line, all right? But I want us to have an idea of what exactly are we doing and why and how this is amazing, right? How this is awesome, right? You could find areas before using squares, right? Using geometry. But in the real world, right? What if you were to ask to find the area of odd shapes, right? What if you were to ask to find the area of something you're out of an odd shape? You knew the function of it, right? You knew, right? You can probably create a function of what it looked like. But what if I told you, hey, find me the area of this? I don't know. All right, we can use the method we did before, right? To get guesstimates. But what if you need it for like an engineering job or a physics job? You needed something precise, right? As long as you know this function, all right, what that curve looks like, you can find the exact area, right? The exact area. Right, so let's just say, hey, you're at a job and they're like, hey, I want you to find the area between 0 and 2, okay, of this function, right? So you know that you would go get the area under the curve. Remember, we're finding the area under the curve, right? And right, you could apply one method we applied before is, hey, I can separate this into shapes that I know. I can find the area here and the area there and add it, right? So for A1, right, we'll call this square. A1, that is base times height. That is 2 times 2, right? Base times 2, 2 times 2, this is 4, right? And we'll call area 2, right? That triangle, which is the base is 2, right? It's base times height over 2, though, right? So this is base of 2 times height of 2, right? Between 4 and 2. This is the distance of 2, and it's a triangle, so this is divided by 2. In other words, this gives me 2, meaning the total area under that curve is 6 units squared, right? Oh, too long, right? A little too long, right? Let's go ahead and apply calculus, right? Let's go ahead and apply calculus. This is the beautiful part of this section, all right? It's amazing. To find the area under the curve, right? You take the integral between the two bounds that you're looking for, between 0 and 2, right? So these are going to be your x values, right? I'm cutting it off from here and here, right? Of a function. Well, my function is x plus 2, right? And that is right there what you need to integrate, right? Let's go ahead and integrate first. Let's see what that gives us. All right, so let's go ahead and apply what we did before, right? The integration of this would be, and this is how I need you to write it. All right, so the integration of that is x squared over 2 plus 2x, right? That is my integral. You're gonna draw this very thin 7, right? And you're gonna translate these points right there, right? Right there, right there. So in other words, this is the integral, right? Bounded between 2 and 0, from 0 to 2. All right. Once you have that, this notation here, this is going to tell you you're going to get the entire function you have here and plug in a 2 minus that entire function again, but with 0 in it. All right. So it's always top minus bottom, top minus bottom. So in other words, this is going to be 2 squared over 2 plus 2 times 2 minus parentheses 0 squared over 2 plus 2 times 0. And a warning, right? Just because your bound is 0 doesn't always mean that your answer there is going to be 0. So please be careful with that. All right. Always show all your work, show all your steps. All right. So finding here, this is 4 over 2 plus 4 minus 0 plus 0. This is 2 plus 4 minus 0. Hey, this is 6. How freaking awesome is that, right? How awesome is that? Come on, right? It's 6. You just found the area under the curve using calculus, right? Using calculus, all right? So you've powered up, right? You've powered up. Like Thanos with the Infinity Stones, right? You've leveled up. With that being said, right? With that being said, whenever you're dealing with shapes, right? Well, whenever you're dealing with the x-axis, and let's just say, right, you have shapes like these. The area above the x-axis, right? The area above the x-axis is going to be positive. Areas below the x-axis are negative. So always be sure to apply a negative value, right? All right, apply a negative value. All right, so in other words, right, for this shape here, they're telling me, hey, I need to find the integral between 0 and 5. So I'm focused on these shapes here. I'm focused on this side here. All right, so the areas is just adding my areas together, right? I'm telling you here that area 1 is 7, area 2 is 4, and area 3 is 1, and area 4 is 1. Right, so in other words, everything that's orange is going to be positive. Everything that is blue, it's going to be negative. All right, everything that's blue, it's going to go ahead and be negative. All right, so in other words, I'm looking here. All right, this is going to be, since the integral between 0 and 5, right? One way you can go ahead and write this as well, right? If it's the integral between 0 and 5, and I know this is split into two shapes, right? Of a function, this is the same thing as the integral between 0 and 3 of that function. Added, let's continue where we left off, between 3 and 5 of f of x dx. Right? It's just continuing, right? It's continuing. Right? I know the entire first part, right? I know this entire first part is going to be, where's that at? Area 1, right, between 0 and 3. Area 1 of that shape is going to be 7 plus, but between 3 and 5, this is under the curve, so that's going to be negative. So this is going to be negative 4, right? Which is 7 minus 4, which is 3, right? Which is 3. Very, very, very nice. And again, have another one here. Okay, right, I need you to find the area between, hey, I want you to find the integral for this function between 0 and 2. Okay, so between here and between there. Okay, hey, I'm gonna have to apply geometry here because they don't give me a function. But I know that from the curve to the x-axis, right, the area between the curve and the x-axis, whether I'm on top or a bottom, that is my area. But I know if I'm below the x-axis, it's going to be negative, right? So in other words, between here and here, let's find this area first, right? That is area 1, right? We'll call it the rectangle. That is base of 2 times height of 1, which is 2. And I got this triangle then. I also got this triangle. All right, that's going to be area 2. That is my base of 2 times height of 1 divided by 2 because it's a triangle, right? So this is going to be 1, right? Meaning finding the total area, right? Both of these are under the x-axis. So this is going to be 3, but more specifically, negative 3, right? Negative 3. So you may be asking, what do I do if it's, all right, what if I do? Oh, yeah, like this next one, right? Oh, and hey, guess what? It's right there, right? Negative 3. So you may be asking, hey, what do I do if I go between 2 and 9, right? Where I have area that is below it and then it transitions to above it, right? We'll take step at a time, right? In other words, I would come here and I would focus on this area first, right? I would focus on that area first. I can draw a perfect triangle from here, right? So for this area 1, this is going to be base of 2 times height of 2 divided by 2, which is the total area under that curve is 2, but it's negative 2 because it's under the curve. All right. For this next shape, right, for this going to the right from here, we're between 4 and over there, I can find the area of this triangle, and then I can find the area of this rectangle, right? So area 2 above the curve, so it's going to be positive. It's base, which is the distance of 2, times height, which is the distance of 2 divided by 2 because it's a triangle. So this is going to be 2. It's going to be positive. And then area 3, it's going to be base of 1, 2, 3, base times height of 2. All right, so this here is going to be 6. All right, so in other words, I'm going to add all these areas together. Right, it's going to be negative 2 plus 2 plus 6, which gives me 6, which is right there. Right. So I was talking about how you can split things up, right? You can go ahead and split things up. You may have to do that whenever we're rewriting integrals, right? Whenever you're rewriting integrals. Right, so for example, here, I'm telling you that, hey, I have this integral between 9 and 26, and I want you to, I'm subtracting the 9 from 19 part of this, what is my new A and B point, right? So one thing I like to tell students is one of them is between 9 and 26. I'm taking away 9 through 19. So let's just say this is 10, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. Almost, right? Almost 26, right? So this is what I had originally, right? I had this original piece. All right. We'll write these up. There's a reason why I'm doing this. Right. So I am drawing 9 through 26. All right. I'm drawing 9 through 26. 9 through 26. All right. I'm drawing 9 through 26. All right. That's what I have right there. That is my first integral between 9 and 26. But I'm taking away everything. All right. Ooh. Sorry, ladies and gentlemen, right there. Right, so I've shaded the entire area. I've shaded, this isn't a graph, right? What I'm shading, this is just a visual representation of what I'm doing, right? So don't think, hey, what are you, what's the height of this? This is just a visual representation. This isn't me finding bases and heights, right? This is just a visual representation. So I've shaded between 9 and 26, and I'm taking away everything between 9 and 19, right? So I'm taking that part off. What are you left with? You're left with 19 through 26. All right, so meaning your new integral would be from the lowest point to the highest point. Always remember that, lowest to highest. All right, and we're going to find out what do you do if it's not written like that. It has to be written like that. If it's not, we'll see. We'll see what do we do, right? So it's between there of this function. So that is what the new integral is, right? So it's like pieces of right, it's just like little pieces laid out, right? You have this, you take that away, what is left over, right? It's just subtraction of areas, right? All right. So we were asking, hey, well, what do we do, right? Let's just say that I say, hey, I'll show you this. If the area between, I don't know, 2 and 5 of a certain function gives me, I don't know, 13, then if you were to flip these points around, right, if we were to go from 5 to 2, right, going backwards of another function, right, of that same function, and this is just going to be negative, right? That's just going to be negative. Meaning if you're given a function where it's the highest point on the bottom and the lowest point on top, well, it shouldn't be like that, right? You can flip this over, but just make sure you put a negative out in the very front of everything. Right. Just please remember that. All right. If I'm asking you to find this, right? So pretty much all we're doing is finding areas, right? You're finding areas. Let's go ahead and use this point again, right? Let's go ahead and use that point again. Let's go ahead and use this graph that we had here. Right? It doesn't matter if your x values are negative, right? Right? It doesn't matter if your x values are negative. Let's just say I wanted to find the area between -2 and 2. Right, so I wanted to find the total region there. All right, I wanted to find this total region. All right, using geometry. The base is 1, 2, 3, 4. 4 times my height. 1, 2, 3, 4. Divided by 2, right? Because it's a triangle, so this is 16 divided by 2. This is 8. All right. It's still above the curve, so it doesn't matter, right? It's still above the curve. Just because this endpoint, right? These endpoints are negative, don't let that throw you off, right? Meaning, if you were to write this as the integral from -2 to 2, that would be correct, right? Because -2 is lower than 2. All right. This function, which is what was the function? X plus 2 dx. All right. I know that my answer there should be 8. So let's go ahead and do calculus, right? The integral of this is x squared over 2 plus 2x bounded between 2 and -2. All right. Meaning this is going to be 2 squared. This is very important. Make sure you always, whenever you're rewriting it, right, whenever you're subtracting the bottom parts, always write things up in parentheses. 2 over square 2 plus 2 times 2 minus parentheses -2 squared over 2 plus 2 -2. There's nothing wrong with having too many parentheses for the most part, right? I'm sure there are some sections out there never say never, nothing's definite like that, right? Have your proof. But write it up in parentheses like that because like I mentioned before, right? The calculus concepts are pretty straightforward. Students understand them. It's just, this is where the majority of points are taken off, right? Steps like here, right? Steps like that, it's just algebra stuff, right? So please, please, please just be very, very careful with your algebra, right? So here I get 4 over 2, which is 2 plus 4 minus, that is 4 over 2 minus 4. All right, so this is 2 plus 4 minus 2 minus 4. Right, I'm being very careful with my signs here, specifically this one and the parentheses on the right, right? This is the importance of having these parentheses here because this negative event is eventually going to have to distribute in there. So please, please, please do not forget that. All right, so I have 2 plus 4 minus -2. Negative times the negative equals A. If you said it out loud, thank you. 2 plus 4 plus 2, which gives me 8. The beautiful part about calculus. Look at that, right? Going back to this question here, tangent again. If I were to ask you, hey, find the area of this under the curve between 1 and 1. 1 and 1. Well, what are you talking about, right? What if I said, find me the area between 1 and 1 of x plus 2 dx, right? Go ahead and plug that in and see what it gives us, right? I'm going to show it to you to see what happens, right? I know that this is x squared over 2 plus 2x bounded between 1 and 1, all right? This here gives me 1 squared over 2 plus 2 times 1 minus, you're already seeing it, like, right? What? These are the exact same things. Why are you writing it? Because I want to show you why, all right? So this here is going to be 1 over 2 plus 2 minus 1 over 2 plus 2, right? One thing you can do is, sure, you can combine these first, or you can distribute, right? Let's go ahead and distribute this negative into there. The importance, right, of having these parentheses always. This is 1 over 2 plus 2 minus 1 over 2 minus 2. These cancel out and these cancel out, leaving me just with 0. Visually representing this, right? It's, hey, I want you to find the area between there and between there. But, hey, there's no gap there. There's no wiggle room. There's nothing. I can't move, right? So in other words, there is no area. The area is 0. So remember, if you're finding the integral, it doesn't matter what the function looks like, right? It can look something weird and extreme, and you may be like, we haven't done anything like these. But as long as these endpoints are the same, it's going to be 0 no matter what, right? It's going to be 0 no matter what. All right. I'm told that, all right, I'm going to go ahead and make this line, right? Hey, you have this integral, right, between -6 and 6. You're adding 6 to 8, but you're subtracting -6 and 1. Like I mentioned before, I'm going to want to go ahead and draw this line. All right, -6, -5, 3, 2, 1. And I'm adding everything all up to 8 is my highest, right? Ooh, another space. That was weird. Okay, something like that, right? You can keep going to the left and to the right, right? So I know that I have a space between, all right? I have a space between -6 and 6. All right, that's what I'm starting off with. I'm starting off with that, right? The first one. I have my integers between -6 and 6. I'm going to add something to that. I'm going to add a segment between 6 and 8, right? So I'm going to attach that there. All right. So at this point, right, my integers between -6 and +8. But I need to subtract now between -6 and 1, right? So if I'm subtracting between -6 and 1, I now have this. Meaning, hey, what are the new bounds of my new integral? Right, the new bounds of my new integral are between 1 and 8. Where A is my lowest point is 1, and B is my highest point is 8. Right. All right, so let's see what we have here. All right, I'm told here that the area, right, I'm going to want to go ahead and do this again. And here I'm actually given actual values, right? So -3, -2, 1, 0, 1. Of course, there's other methods out there to do this, right? But I think for the most of us, we're really used to seeing things visually, right? Visual representation, so that helps, right? So I'm told that the area, and I want us to think about this, right? The area between -3 go ahead and color coordinate this, right? I'm told that the area between -3 and 6, right? I'm told that this area, right, is 15. I am then told that the area between 3 and 6, right, specifically this point here, is 8.7. Right? How do you find the area between -3 and 3? I want you to think about that for a minute. If the entire piece is 15, if that other little part is 8.7, what is the area of the other part? Right, so you'd say, right, it is A total minus the difference in areas, all right? Minus your difference in areas, right? So in other words, this is going to be mathematically, right? This left piece added to the right piece should equal the area of the entire piece, right? Meaning you would go ahead and solve for x, right? And what does that give me? Right, I end up getting 63/10, which is 6.3. Right. And this is an area, right? We're dealing about area, so probably my curve looks something like that, right? Where the far right point had a big chunk, right? 8.7 in the entire. This other left part was less area, right? Between there and there, but it was 6.3. Right. Yeah, that is all I have for y'all today. And thank you very much for your time, and I hope you enjoy the rest of your day. Thank you.